Okay, so back from that tangent, Lewis structures. Representing valence electrons with dots, I think I skipped something. There we go, one of two. So the valence electrons are the ones that are the most important in chemical bonding because those are the ones on the outside of the atom. And so those are the ones that are going to interact with other atoms. In the highest principal energy level, they're the most loosely held. So in a Lewis symbol Lewis symbol for an element, we show the chemical symbol and surrounded by dots for the valence electrons. Let me just set up right now. So writing the Lewis symbol for oxygen, we start by just drawing the element symbol. So O for oxygen. And then we need to know how many valence electrons does oxygen have. You look at the periodic table and see what group is it in. It's in group 6A. It's got 6 valence electrons. Six dots. So we generally do the dots either on the top, on the bottom, on the right, or on the left. And so we don't want to see something like this because it's hard to look at that and see how many dots there are, right? So that's not so great. It's a little bit like dice, right? I remember playing Monopoly with kindergartners. Well, it was just the one kindergartner and me. But on regular dice, the pips are all in the same pattern every time. And so you look at that and you can just say, that's 6. The kindergartner doesn't recognize that yet, and they get their finger out and they count all the little dots. That's an excellent question. Does it matter what order you put them in? No, it doesn't. So I could have the paired ones like that. I could put the paired ones over here and the unpaired ones over there. It doesn't matter. Correct. I wouldn't put just 3 pairs and have one side empty. So I don't always draw it this way because it often ends up a little bit lopsided. But the idea is that you put one on each side first, and then you pair them up. But then they don't end up being very centered, and I don't like that.
And that's because the electrons are repelling each other as they're equidistant.
Sort of. So the Lewis theory doesn't really explain about where the electrons are or exactly what they're doing or anything, but it does tend to match up with some things from quantum mechanics. And it's not really it wasn't intentional, but it's not an accident either because they're just both describing true things. And so when we get to valence bond theory, then we'll see, oh yeah, that's really kind of cool how that all works out. I will tell you a thing that's not in the textbook. So, well, let's cross that one off because that one's not right. But these others, no matter how I draw them, if I put one on each side and then pair up as necessary, I'm going to end up with 2 electrons that are unpaired when I draw the symbol for oxygen. And these are the electrons that are going to be shared with another atom. So I look at this and I say, well, oxygen's probably going to make 2 bonds. And it is. And if I look at chlorine and draw its Lewis symbol, it has 1 unpaired electron, and chlorine usually makes 1 bond. Now, it doesn't mean that oxygen can't make just 1 or have 3 bonds. It's possible, but when we talk about formal charges, we'll see that it would rather not. So that's kind of a preview of things to come. So here's a summary of the instructions about the dots. We place them with a maximum of 2 per side. It's just a simple way to visualize the number of valence electrons. I can. Good. So the top, bottom, right, and left works out really nice, because if you have pairs in those 4 places, then you have 8 valence electrons. And what do the noble gases have? 8 valence electrons. What is everybody wanting to get? 8 valence electrons. So the ions form so that the atom as an ion has 8 valence electrons. But if you've got nonmetals that nobody wants to give up and be a cation, then they're going to share electrons to have 8. And so we have what's called the octet rule. Atoms transfer or share electrons to achieve an octet of valence electrons. So an octet is 8, just like 8 people singing together is an octet. And of course, helium and hydrogen are going to be exceptions. They are too small, they couldn't handle 8 electrons. So helium has a duet of electrons, it's cool all by itself, and hydrogen just wants to be like helium, it just wants to get 2 electrons. So we can look at ionic bonding with Lewis symbols. So we can draw Lewis symbols for potassium and for chlorine. So the symbol for potassium is K, and how many valence electrons does potassium have? It has 1, it's in group 1, so 1 dot. And then chlorine is Cl, and how many valence electrons does it have? 7. 1, 2, 3, 4, 5, 6, 7. Okay? Now, neither of these atoms is happy, right? We talk about them being happy. 8 electrons makes an atom happy, and we want to make everybody happy. The nice thing about this is oftentimes we can make everyone happy, and then we feel happy about making the atoms happy. So we talked about ions and their electron configurations, and how this potassium atom is going to lose 1 electron, right? Here we have the electron configuration for the potassium atom, and we see it's got this 1 valence electron here. It's going to lose that 1 valence electron. When it does that, does it now have 0 valence electrons? No, it doesn't, because it's got now the next shell underneath is going to be exposed, and that's an octet down there. When you peel off the incomplete layer, underneath is always an octet. Now, in the Lewis structure, I'm going to take this electron away from it, and it's going to look like the potassium doesn't have anything. But I know that under that 1 electron, it's got an octet. So I don't want to, when we start, we have a certain number of dots, and we're going to have that many dots at the end. We're not going to suddenly show dots from lower layers coming in. We're just going to look at all the original valence electrons, and we're going to be okay with not showing the rest. But when I take the electron away from potassium, that doesn't mean now it's got 0, and why is it doing that? Because that's not 8. It's got 8 underneath. We're just not going to show them. So this potassium, in order to be happy to get 8, needs to lose an electron. Well, the electron can't just go off into space, it has to go somewhere. And here's this chlorine. Chlorine's got 7 electrons, it wants 8, and it's like, hey, I'll take that electron. So that's what happens, is potassium transfers its electron to chlorine. Yeah, there are energy changes involved in this, and we'll talk about those in a minute. We're not going to talk about it just yet, but really soon, that's where the lattice energy thing comes in. And you probably wish I hadn't told you about that when we get there, but you asked. It's your fault now. But this now has a charge on it, so we can't just ignore that. So that's a positive charge, and the chlorine here is a negative charge. And you can kind of imagine that minus sign could get lost in the dots. right? That'd be pretty easy to do. So what we usually do is we put big brackets around the dots, the symbol with all the dots, and we write the charge on the outside. For the cation, we don't need to do that because we took all of its dots away, and so we can just put the plus there. But the anion's always going to end up with 8 dots, and then we put the charge on the outside. So now we have a positive ion and a negative ion, and the opposite charges attract, and we have this electrostatic attraction, and that's the ionic bond. Any questions? Yeah, so the ionic bond, we transferred an electron, and now we have a positive ion and a negative ion.
Okay.
And they're attracted to each other. It's like, ooh, now that you have that extra electron, you're really hot. I want to be with you, right?
That made you so good.
Hmm?
That made you so good.
Yeah. Yep. That was just the thing you needed. Okay, so let's do this. This helps us to understand, but I won't ask you to do this on an exam because there have to be talking involved or motion or something. Use Lewis symbols to predict the formula for the compound that forms between magnesium and nitrogen. So I tried something different yesterday and it didn't work out very well, so I'm going to go back to the other way. So we got magnesium and we got nitrogen. Let's see, I think magnesium's going to be purple. No, magnesium's going to be green. So there's magnesium. How many valence electrons does magnesium have? 2. 1, 2. Nitrogen's going to be blue. So here's nitrogen. How many valence electrons? 5? 1, 2, 3, 4, 5. So here we have a magnesium atom and a nitrogen atom, and it's a metal and a non-metal, and so the metal's going to give electrons to the non-metal, and we're going to see how we could work it out. So the nitrogen is trying to gain 3 electrons. The magnesium's trying to lose 2 electrons. So magnesium's like, hey, anybody want these electrons? And the nitrogen's like, yeah, I want them. Okay, cool, you can have them. I can do this with atoms. I had the worst time doing it with Hot Wheel cars with my kids. Could not get into the Hot Wheel cars talking to each other. So the 2 electrons from the magnesium were given to the nitrogen. Now these things aren't atoms anymore, they're ions. So this nitrogen has what charge? 2 minus, because it gained 2 electrons. And the magnesium is 2 plus. So are either of these guys happy? The magnesium's happy, so I'm going to make him pink. Is the nitrogen happy? Not quite. Needs more electrons. Well, if there was 1 magnesium atom there, there's probably 50 gazillion other ones. So let's just bring in one of the other ones. So this magnesium also has 2 valence electrons, right? And so this nitrogen is like, hey, can I have one of those? Magnesium's like, you can have both of them. No, I only want 1. Oh, okay, it's better than nothing. So take that over there. And now this magnesium has a +1 charge. And the nitrogen has a 3 minus charge, right? Is the nitrogen happy? Got 8 valence electrons. Yay, pink happy. Is magnesium happy? Nope. Dang. Magnesium needs to find somebody to take this other electron. Well, you know, if there's 1 nitrogen, there's 50 gazillion other nitrogens, so let's draw one of the other nitrogens. Also has 5 valence electrons. So the magnesium can offload this electron to this nitrogen atom. Whoops, that didn't work out very well. So now this nitrogen has a -1 charge. And what's the charge on the magnesium? 2+. Did that make anybody happy? The magnesium, right? Got rid of its valence electron, so underneath is that nice complete shell that we're just not showing. Is that nitrogen happy? No. This is going to go on forever, isn't it? We're almost there. The end in sight. This reminds me of my grandma Johnson, who at family dinners, bread and with it. So you'd have, butter and jam. We'll skip the butter. Just, some nice homemade jam and dinner rolls. And so, you pass the stuff around. We actually sat down and passed the food around. And so you take a roll and you take some jam. You kind of estimate how much you need, but it never comes out right. So you have the bread and you put the jam on it, but there's some extra jam. So then she really likes eating. So, I've got extra jam. I need another piece of bread. So then you get the bread, but now I don't have enough jam. And you can go on all day long if you want to this way, eating bread and with it. And that's what this reminds me of. Well, I've got too much of this. Now I need one of the other. And we go on and on and on, but eventually it does come out even. And it's going to come out even right now. So brought in another magnesium atom, and it can give an electron to nitrogen, and give another one to the nitrogen. And now this magnesium has a 2+ charge, and it's happy. Yay, happy. And what's the charge on this nitrogen? 3-, because it got 3 extra electrons now. And it's happy, and everybody's happy. But it took 3 magnesiums and 2 nitrogens for this to work out. If we had one less of anything, it doesn't come out right. And we can do more, but it's always going to be this ratio. 3 magnesiums to 2 nitrogens. And so that's why the formula is Mg3N2. Because that's the lowest ratio of those elements in order for it to be good. Any questions? So that's what's behind the whole crisscross idea, or least common multiple, or however you're thinking about making ions. So someone asked about energy. Well, when you form an ionic compound, it's generally quite exothermic. A lot of energy gets released. We just got done studying thermochemistry a little bit, and so here we've got sodium and half of a chlorine, a mole of sodium, half a mole of chlorine makes sodium chloride. And we can look this up. The heat of formation for that is -411 kilojoules per mole. So where does that energy come from? Well, we could look at the first ionization energy for sodium. To make sodium into an ion, you have to invest or give it 496 kilojoules. And then the electron affinity for chlorine is exothermic, so that's going to release 349 kilojoules for every mole. But if you look at the sum of these, just transferring the electron, we end up with this absorbing 147 kilojoules when it actually releases 411. So electron affinity and ionization energy do not explain the total energy change in this reaction. There's a piece missing, and that piece is lattice energy. So the lattice energy is the energy associated with the formation of a crystalline lattice of alternating cations and anions. And it's measured from the ions in their gaseous state. So we've got separate cations and anions, and they're going to be attracted to each other. And when they come together, that lowers their energy. Well, where does the energy go that they had? It gets released. That's the lattice energy. It gets released as heat. So this is an important idea. The formation of ionic compounds is not exothermic because the metal wants to lose an electron and the nonmetal wants to gain an electron. I talk about it that way. Go ahead and think about it that way. That's only a small part of it. That doesn't account for the lowering of energy of the formation of this compound, because it costs more to take the electron away than gets released by giving it to the nonmetal. The heat that gets released, the reason that this is exothermic, is when the cation and anions come together when they coalesce into a solid. So this is illustration of what I'm trying to describe. So here we've got all these separate cations and anions. The purple ones are the sodium ions and the green ones are the chloride ions. And they're attracted to each other, and you can kind of imagine this happening kind of like with magnetic pieces or something, or like Iron Man. Iron Man's suit comes together like this, right? And they fly from all over the place. It comes together and arranges itself like this. It arranges itself this way because this is maximizing the attraction between negative and positive ions, minimizing the repulsion between positives and between negatives. And when it comes together like this is a lower energy state. And so if it's lowered in energy, the energy that it had when it was in the higher energy state has to go somewhere. And that's what gets released as heat into the surroundings. So that's what lattice energy is. Any questions?
It would be anything forming this, we wouldn't be able to like reference it in our lives. We're like, oh yes, we felt this heat. Like it wouldn't be anything large enough to do that, right?
Well, we would not experience that, but the heat involved here is very definitely enough to be felt.
Okay.
Yeah.
There's a really cool picture of like solid sodium reacting with chlorine gas, and it's just sparking.
Yeah. It's like
really cool.
very vigorous, explosive in some cases. Yeah. But in terms of macroscopic objects coming together to do this, that's harder. Yeah, that's harder. Well, how do we know what that lattice energy is? The easiest way to do this is using what's called a Born-Haber Cycle. And this is using the idea of Hess's law. And Hess's law, remember, is that the change in enthalpy, because it's a state function, it doesn't matter how we get from the first place to the second place. It just matters what the difference is. And so we can take other reactions where we know the enthalpy changes, and if we can combine those and add them up to the equation we want, then we can add up the enthalpy changes and we can predict the enthalpy change for this reaction that we don't want to actually do and study, but we just want to know what the change is. So in the Born-Haber cycle, we're doing a very similar idea. This is a hypothetical series of steps where you're starting with the elements and you're making them into ions, and then you're putting them back together again. So it looks like this for sodium chloride. And if you're looking down, taking notes, you need to look up and just watch the arrow here, because this can be really confusing. So where are we starting? We're starting right here in the middle. Well, it's not really the middle, but that's where we're starting. So we've got sodium element, solid, and half a mole of chlorine. Those are the elements in their standard states, right? So we want to know the lattice energy for when the sodium ions and the chloride ions in the gas state come together to form sodium chloride. That's not something that we can measure directly. You can kind of imagine that would be kind of tough to measure. We can measure the enthalpy change, though, the heat of formation for sodium chloride. It's been measured. We can just go look it up. Even in your textbook, you can look it up. So, to find out what this is, we're going to identify all these other changes, and then this is the missing piece. So, we imagine taking sodium solid atoms and making it into atoms in the gas state. That requires you to put some energy in, and you can figure out how much that energy is. And then we're going to take this half a mole of chlorine molecules and separate them and have 1 mole of chlorine atoms. So we're going to break that bond in there. And so we can look that up, figure out what's the energy change for that. And then we're going to make the sodium atoms in the gas state into sodium ions by taking an electron off. And so we can look at the ionization energy, so we can figure that one out. And then we're going to take this chlorine atom and put an electron on it to make a chloride ion. Well, that's negative. That's exothermic, the electron affinity. And so then this is going to start coming down in energy a little bit. All of these pieces are known. And so this is the missing piece, and we can find it by difference. That's the lattice energy.
Where is the electron source instead of what?
So, yeah, where is the electron source? Well, when this actually happens, the electron source is the sodium.
Oh.
The electron goes from the sodium into the chlorine.
Okay.
But when we're doing this hypothetical stuff, we could just say, well, it's going somewhere, and then we're going to bring it back from somewhere later. Any questions about that? So, we looked at how the ionization energy and the electron affinity for sodium and chloride, those did not add up to explain how this was a negative energy change, how this was exothermic. Because that actually, these two things put together actually predicts it slightly endothermic. But the reason the overall change is exothermic is that even though we have several endothermic changes and one small exothermic change, when we get those ions and they all go and come together, they kind of make that sound, they give off a lot of energy, and that makes up for all the other investments. Yes?
So, sorry, which is the bit that we don't know?
The piece we don't know is this piece right here.
Okay, gotcha.
The lattice energy.
Right.
That's the thing we can't measure.
Right.
So we measure
Okay. Everything else.
all the way around, and then we can
Solving
figure out.
for-
Yeah. Because this overall change has to be the sum of these other things. So we've got an x in here, but we know the total, and so we can find out what x is. So now that we know kind of what lattice energy is, there's trends in lattice energies. Yay. So here we're going to look at metal chlorides. And when we compare things, we want to be careful what we're comparing, because when you have a bunch of things changing, you can't tell what is really having the effect. So we like it if there's only one thing changing. So here we've got lithium chloride, sodium chloride, potassium chloride, cesium chloride. These metals are all alkali metals, so they're in the same family, they're similar, and we're looking at them with the same anion. So here we have depicted over here illustration of the relative sizes of these ions. And I noticed this yesterday. What's odd about that picture? Why is potassium not purple like the other ones are? I mean, is there some significance to that, or was that a drawing typo?
Oh, you're actually asking.
Yeah, I'm actually asking
I
this.
don't know.
You know, why is that one different? I just want to know, why did they draw that one different? I mean, if they drew all of them different colors, I'd be, well, yeah, they're different elements, make them different colors. But why is potassium the silvery gray color and the other three are exactly the same color?
Well, maybe they're not the same color, maybe they're different shades of purple.
Maybe they are different shades of purple. And actually, the lithium looks like it's maybe a little lighter and shinier, but so we're just really getting way too far into this. Yeah, so sorry. That was a squirrel. These are the lattice energies for when lithium and chloride come together from ions in the gas state to form the solid. So this one gives off the most energy, 834 kilojoules, 788, 701, 657. So there's a trend here, right? As we're going down this group, the lattice energy is getting smaller. What's up with that? Well, let's look at the atom size, or the ion sizes. So the chlorines are all the same size, but these cations are different sizes. As we go down the group, they get larger. And so here what we're showing is the distance between the nucleus of lithium and the nucleus of chlorine. 241 picometers, 276, 314, 348. So the distance between the two things is getting larger. And this comes back to Coulomb's law. So Coulomb's law, E is proportional to 1 over R. I really should probably fix that because that slash doesn't mean fraction to some people. So that means that the larger the radius, the smaller the energy. So negative energy here is the more energy being given out. So smaller energy means they're not as attracted to each other. So this is getting closer to 0. So cesium and chlorine ions cannot get as close together as lithium and chlorine because the lithium ion is smaller and it can snuggle in closer to the chlorine than the cesium can. And the attraction between these two depends on the distance between them. Okay? So if the ion sizes are larger, then the lattice energy is smaller.
So each compound has its own required amount of energy that it needs to just exist, and anything excess, they just get rid of it.
Say that again.
So the amount of energy that's exchanged between lithium and chlorine for that to exist is different than the amount that is required for sodium and chlorine. And so there's a certain amount of interaction between those electrons that's required for those to exist, and all of the excess is emitted.
I think I understand what you're trying to say,
That's good.
but I'm not positive.
I don't think there is excess.
So what we have to remember what the lattice energy is. This is, we've got separate lithium ions and chloride ions in the gas state, and as those come together, that's a lowering of their energy, and this is the energy that's lost to the surroundings. It's given off, the lattice energy.
So there's a bigger difference between those energies because of the size of the...
So these are much more excited to get together than these two are.
Right, okay.
Yeah. So this number here is related to this number.
Okay.
And then, of course, the negatives make things confusing. Because sometimes we think of, well, minus 834, that's smaller than minus 657. But we're talking further from 0. It's bigger. We can also look at what if the ions are the same size but their charges are different. And so here, another piece of Coulomb's law, the energy is proportional to Q1 times Q2. So here, sodium and fluoride, the distance there is 231. Calcium and oxide, 239. Not exactly the same, but really close. But the charges are different. This is +1 and -1. So we have Q1 is +1 and Q2 is -1. So we multiply those and we get -1. Here we've got Q1 is plus 2 and Q2 is minus 2. We multiply those, we get minus 4. That predicts that the energy for this one is going to be 4 times as much as for this one. And here we've got minus 910 and minus 3,414. Well, if this was minus 900, minus 3,600 would be 4 times. That's actually pretty close, because there's other things going on as well. But the lattice energy depends on the magnitude of the charges. So if we have larger charges, they are going to rush together much more than if we have little wimpy charges. So it's the distance between the ions, the size of their ions, and the charges. Those are the two things that affect the lattice energy. The ion charge has a bigger effect. Lattice energies become less exothermic with increasing ionic radius. So less negative. Lattice energies become more exothermic with increasing magnitude of ionic charge, more negative. So these are fun mind benders. Arrange the following in order of increasing magnitude of lattice energy. Lithium bromide, potassium iodide, calcium oxide. They're all different. Well, let's just look at them here. So I've got lithium. We need to look at their charges and their sizes. So I have lithium and bromide. I have potassium and iodide. And I have calcium and oxide. And we're not going to look up actual radius of the ion or anything. We're just going to go with periodic trends. So what's the first thing you notice that's different about those three? One of these things is not like the others. One of these things just doesn't belong. One of these things is not like the other. Can you tell me before I finish my song? Something like that. You're not gonna say it. The last one, calcium oxide, the charges are different, right? Here's plus 1, minus 1, plus 1, minus 1, plus 2, minus 2, right? So if we're looking at the product of the charges, we've got plus 1 times minus 1 is minus 1. That run into itself. Minus 1. Plus 1 times minus 1 is minus 1. And here we have plus 2 and minus 2, and that's minus 4. Based on charges, which of these has the largest lattice energy? Calcium oxide. The prediction here is if the sizes are the same, this is going to be 4 times as large. So this question says in order of increasing magnitude. So we're going to go with the smallest, then the medium, and the biggest. So I'm going to put my less than, greater than signs up here. And I'm going to predict that calcium oxide has the largest lattice energy because the charges are bigger.
And you said that was the most important.
That's going to be a bigger effect than the radius, because here we have the two charges are being multiplied, and the difference in the size is it's 1 over the distance. And so in order for that to have the same effect, the difference in size here would have to be a factor of 4. And so that's probably not going to happen. So then what do we do with the rest of them? How do we tell the difference between lithium bromide and potassium iodide? The charges are the same, so then we're going to look for sizes. So we're going to look for potassium and lithium. So which is bigger, which is smaller? Yeah, so potassium's bigger and lithium's smaller. Experimenting with a way to indicate that. And then for the anions, we've got bromide and iodide. Who's bigger? Iodide. Who can get closer together? The small ones, right? So because these guys can get closer together, the attraction is greater, the lattice energy is larger. So lithium bromide is in the middle here. And the potassium iodide would have the smallest lattice energy. They can get closer together. So E is proportional to Q1, Q2 divided by R. If R is small, then E is big. If R is big, then E is small. You also think of a magnet on the refrigerator, and you're going to stick up one piece of paper, or you're going to stick up 10 pieces of paper. Which is going to stick better? One piece of paper. Why? Because the magnet can get closer to the refrigerator. 10 pieces of paper, it's not a real thick, it's not a real big distance, but for the magnet it is. It's 10 times. The calcium oxide is greatest because the Q1 times Q2 is bigger. And then we could look and see, well, how do the sizes of the calcium oxide compare to the other one? Well, here's oxygen, and here's calcium. So calcium's going to be similar in size to potassium, a little smaller, but not a heck of a lot. And then over here, oxygen is smaller than these two. And so this being smaller is just going to make that bigger. And we already decided it was the biggest, so that's not going to be a problem. And I wouldn't give you ones where there's lots and lots of different factors. This is about as complicated as it would get. Compare things with the same charges, decide on size, based on size. Compare things with different charges, do it based on the charge.
So smaller the ion,
The stronger they stick.
The more they stick, the closer they get, the higher the
Lattice energy. Mm-hmm. So then it's always good to see, do our models match up with reality? They do. So does this bonding model predict a high melting point for sodium chloride? Sodium chloride does melt, but you have to get it super, super hot. So because it takes so much energy to melt this, that tells us that these bonds must be strong. And these bonds are also non-directional, meaning this chlorine atom is attracted to chloride ions, so the sodium ion is attracted to chloride ions on all different sides of it. It's not just into one other. That contributes to the high melting point. The solid sodium chloride is not conductive. Here you've got solid sodium chloride, and you have this conductivity apparatus, and you stick it in there, a light bulb doesn't go on. There are positive and negative charges here, but they can't move. They're stuck, they're frozen, literally frozen. If we dissolve this, then we allow the ions to move free of each other, and then we do see electrical conductivity. If we melt this and form a liquid, molten sodium chloride conducts electricity as well, because again, the ions can move.